Hello, so in this video we're going to look at finding the derivative of the function r cosec of x. So if we remember from previous videos, we've got this sinh function or this hyperbolic sine function, and we've got this cosec function, which is just defined as 1 over the hyperbolic sine function. And so the arc, or I should say the r cosec function. So that's just defined as the inverse of the cosec function, and I'm just gonna denote this by a -1 there, like that. So it's the inverse of the cosec function, and we want to find the derivative of this r cosec function in this video. And it's very similar to how we found, well, this method that we're going to use in this video is very similar to how we found the derivative of the arc cosec function. So not the arc cosec, the arc cosec function, the trigonometric function. So obviously this one here is a hyperbolic function, and these are all hyperbolic functions. So yeah, the process is as follows. So if we let y be equal to r cosec of x, we can apply the cosec function to both sides to get this, and then our right hand side is going to become x, because cosec is the inverse of the r cosec function. And then we can now differentiate both sides with respect to x. So therefore the derivative with respect to x of cosec of y is going to be equal to the derivative with respect to x of x. And we know the right hand side there, well, that's just going to be equal to the number 1, because differentiating x with respect to x just gets us 1. Okay, great. So if we go to a new page then, so d by dx of cosec of y equals 1. And similarly to what we did in multiple previous videos, we're differentiating a function of y, and that y function is a function of x itself. This is a chain rule problem. And if we apply the chain rule, this is what we're going to do. So we're going to differentiate with respect to y, the cosec y, and we're going to multiply that by the derivative of the y function with respect to x, because of course this y there is a function of x, namely the r cosec function. And obviously this all equals 1. So now we've got to, and let me just make a note here that this is by the chain rule. So just applying the chain rule that we have done in many previous videos before. So now we want to differentiate the cosec y function with respect to y. So from a previous video, we know that when we differentiate the cosec function, we should just get negative cosec times by coth, the hyperbolic cot function. So using this this result there that we proved in a previous video, we can just apply that here. So we're now going to get negative cosec y coth of y times by dy by dx, and that's equal to 1. And of course, what we could do is just divide both sides by the negative cosec times by the coth. And if you do that, you will get dy by dx equals 1 over the negative cosec of y times by the coth of y. And I'm just going to move this negative up to the top there. So let me just rub that out there and put the negative sign up there, because that's exactly the same thing as we had. Great, so we've got this then. And obviously, as we know, y is the same as r cosec. So therefore, what we know is the derivative with respect to x of the r cosec of x function will be this there. So let's go to a new page and write that in. So d by dx of r cosec of x. Sorry, there shouldn't be a c there. It should be just a r cosec of x. So that's going to be -1 over cosech y times cof y. Okay, so obviously we're differentiating a function of x. We get a result which is a function of y. We've got to eliminate this function of y to get a function of x. And we can do that because, well, firstly, if we go back here, we know that cosech y equals x. So we can just substitute that in. So we're going to get here a -1 over x times cof of y, because as we know, cosech of y is equal to x. Let's just make a note of that there. So we're going to get x there, and then this cof of y function. And we know from hyperbolic identities, so obviously we know the identity cosh squared y subtract SINE or sinh y squared equals 1. So we know that identity. So dividing everything by hyperbolic sine, what you would get is you would get hyperbolic, divide everything by hyperbolic sine squared, I should say. Then you're going to get cof squared of y subtract 1 equals cosech squared of y. And rearranging this to make cof the subject to the formula. So you get cof of y equals the square root of 1 plus cosech squared of y. And of course, as we know up here, cosech of y is just x. So cosech squared is going to be x squared. So that equals 1 plus x squared. So we can just plug that in there. So we get -1 over x times the square root of 1 plus x squared. So, okay, so we get this answer there. So this is actually very similar to when we differentiated the arcosech function, so the trigonometric function. And we got a result which looked like this. And if you remember from that video, we actually put a modulus symbol between the x there. And the reasoning that we had for that arcosech function was we had to put the modulus sign there because we had to make sure that this function was negative for all values of x in the domain. And in fact, we're going to do the same here. So we're actually going to put the modulus sign there. So why must we do this? Well, again, let's just look at the graph of arcosech. So, I mean, let's just start with the graph y equals sinh of x. So we know that graph kind of looks something like this. So, but by the way, that's just the graph, exactly the same graph as a half of e to the x subtract e to the -x, because that is exactly the same as what sinh is. So that's that graph there. So we've got an infinite domain from -infinity to +infinity. Okay, so now let's consider the cosech function. So cosech, which is just 1 over the sinh function. So 1 over the sinh function. Sorry, that should be an x in there. Okay, I mean, if you divide 1 by 0, you're going to get, well, technically infinity, an undefined value, I should say. So therefore, we're going to start from the positive real axis. We're going to start from somewhere up there, and we're going to keep on going down and down and down until we tend to 0. And then in the negative real axis, again, as we get closer and closer to 0 from the negative side, we're going to tend to negative infinity. So something like this will be the the cosech graph. So the arcosech graph, which is the inverse of the cosech graph. So that's going to kind of look actually very similar. So if we just put in a y equals x line in between there, so this is the line y equals x, and we reflect this graph, so we're going to get something eerily similar, so something like this again. So that kind of shape there. So what do you notice? Well, we notice that the gradient of this function in the negative part of the domain is negative. So all these tangents have a negative gradient. And the same thing here. So all these tangents in the positive part of the domain have a negative gradient too and slope downwards. So what can we tell from this? Let me just put the bracket up there. So we can tell from this graphically that d by dx of r cosech of x must be less than 0 for all x in the real numbers. So for all real values of x, well, apart from 0 where it's undefined, I should say. But apart from that, all values of x will give a negative derivative. So if we go back to this here, so I mean, if we just remove the modular sign to start with, so let's analyze this function. So we've got a negative number on the top. Okay, that's fine. Let's look at this square root here. So we're square rooting 1 plus x squared. So pick any number, any real number you like, square it. Well, that's always going to be greater than or equal to 0. So that bit's greater than or equal to 0. Then we're adding 1. So you're adding 1 to a number at least as big as 0. Well, everything inside that square root is going to be bigger than 0. So you're square rooting a number bigger than 0. So therefore, that answer there is going to be bigger than 0. So that inside the square root is bigger than 0. So the square root is going to be bigger than 0. So that is all a positive. So, okay, we want a derivative which must be negative. We want this function to be negative for all values of x. We've got a negative on the top, a positive on the bottom. So this thing there has to be positive. We've got to ensure that that is positive in order for us to get the gradient we need, which is negative for all values of x. So obviously, if x is a negative number, well, that's going to be negative. You get a negative times positive. That would be a negative. A negative divided by a negative gets you a positive. So that's not going to work. We have to make this x positive for all x values. That's why we've got to put the modular sign in there in order to guarantee we get a positive number on the bottom and a negative on the top. Negative divided by positive gives us the negative that we want. So we can therefore conclude that the derivative of r cosech of x has to be -1 over the modulus of x multiplied by the square root of 1 plus x squared. And that is the result.